Welcome back, everyone. Our first speaker this afternoon is Peterson from University of Florida, and he's going to tell us about quantum walks on Cayley graphs.
Okay. Well, thank you, Ada. And yeah, so first of all, I'd like to thank the organizers for inviting me to this very nice workshop. And also, I'd like to thank all the previous speakers for their very nice talks and stimulating discussions. So let me share my screen and see. Can everybody see that?
Yep.
Okay, good. Okay, so I want to talk about quantum walks on finite groups. So a lot of what I'm going to talk about is joint work with Julien Saucy. And so I'll start with some basic definitions and background. So a lot of the general theory, which I'll be talking about, has been developed in greater generality, say in the context of arbitrary graphs or graphs in association schemes, in the book of Gabriel Coutinho and Chris Kodzil, and in papers by Ada Chan and Gabriel, Chris, and other people as well. But I'm going to sort of take specialize those results to Cayley graphs, and certain results simplify, and in certain cases we can get slightly stronger results. But that's not really the main purpose of doing this. My main purpose is to try to formulate the results and the conditions in terms of characters in such a way that facilitates looking for examples by checking character tables. That's really the aim. Okay, so let me begin with the definition of a continuous time quantum walk. So let A be the adjacency matrix of any graph. Let's say a simple graph. Then continuous time quantum walk on gamma is defined by this family of unitary operators, U of t, e to the ita, where t is in real numbers. So I think Ada had e to the minus ita, which is probably more correct, but I sort of just absorbed the minus sign into the t, which I think quite a lot of people do. So hopefully that won't cause any confusion. And this is operators acting on the vector space span with a basis the vertices of the graph. Okay, so this is the basic setup, and then we're interested in certain phenomena. So we say that gamma has perfect state transfer from vertex A to vertex B at time tau if the BA entry of this unitary matrix has absolute value 1 at time tau, right? So in other words, so in that case, the other entries in the column A will all be 0 because it's a unitary matrix. Right? So that's perfect state transfer. That's one thing we'll be interested in. The other thing that we're interested in, which is one of the main themes of this workshop, is instantaneous uniform mixing. So gamma has instantaneous uniform mixing at time tau if for all A and B in the vertices. So this unitary matrix U of t at time tau, all its entries have the same absolute value, which has to be 1 over the square root of the number of vertices. Okay, so then of course the basic questions that we'd be interested in are which graphs admit perfect state transfer and instantaneous uniform mixing. And so we're sort of looking for examples, and we're looking for necessary conditions, sufficient conditions. Right? Okay, so that's the general setup. Now we sort of specialize to Cayley graphs. So that we can consider a Cayley graph on a group G, finite group G, and we're going to consider normal Cayley graphs. So the connecting set S will be a union of conjugacy classes, and we assume that it's closed under inversion so that we don't have a directed graph, we just have an undirected graph, and the identity element is not in S, so that we don't have any loops in the right. Okay, and of course this graph is connected if and only if S generates the group. Okay, so this is probably familiar to everybody here, right? So this graph will be a graph in what's called the conjugacy class association scheme. So the classes in the conjugacy class association scheme are the conjugacy classes, case of I, say, and we say that G is I related to H if G inverse H is in the ith conjugacy class. So in general, this is not a symmetric association scheme, but the Cayley graph, because we're assuming that S is closed under inversion, will be actually inside a sort of the obvious symmetric subscheme. So that means that we can still apply results about symmetric association schemes to the Cayley graph. Right? Okay, then the eigenvalues of the associations, well, the eigenvalues of the graph, they come from the irreducible characters of the group. Each irreducible character gives the eigenvalue theta sub chi, which is the same formula as Karen had in her talk. And of course, theta sub 1, corresponding to the principal character, is just the size of S. And then we also have idempotents in the scheme. So, in Raghu's talk, he wrote down the formula for the idempotents in the central idempotents, primitive central idempotents in the group algebra, and this is the same formula. So we can view this idempotent as either an element of the group algebra, sort of abstractly, or we can think of it as a G by G matrix. So then it would be a matrix in that association scheme by applying the regular representation of the group. Okay, and sometimes there are advantages to viewing it one way, and sometimes there are advantages to viewing it another way, the other way. So it's good to keep both points of view in mind, as we'll see in a little bit. Okay, now for each eigenvalue theta, we sort of collect together all the irreducible characters that give you the same eigenvalue. Right? Call that x of theta. Right? And then the idempotent projector onto the theta eigenspace will just be the sum of all those idempotents, all those primitive idempotents that give the same eigenvalue theta. Okay. Okay, so next I want to talk about strong cospectrality. So strong cospectrality is a concept that is important in studying perfect state transfer and other phenomena. So the definition is this: two distinct vertices, G and H, are strongly cospectral if and only if for every eigenvalue the projection times G, the projection of G is plus or minus the projection of H. Right? So if you like, this is the Gth column of the projector matrix, and it's going to be plus or minus the H column of the projector matrix. This is a necessary condition for perfect state transfer, and also for a related phenomenon called pretty good state transfer, for those people who have heard of that. Also in the continuous time model, and also in some discrete models, strong cospectrality is a necessary condition for both perfect state transfer, however that's defined, and pretty good state transfer, however that's defined in these discrete models. So I just wanted to talk about that this concept for a little while. So if G and H are strongly cospectral, then there exists a central involution such that H is equal to Z times G. Okay, so normally this is not true for association schemes in general, but in the case of the Cayley graphs, we get this slightly stronger result that if we have two elements that are strongly co-spectral, then they're just related by a central involution. In particular, that has to be a central involution in the group for strong co-spectrality to occur. And here's an example. I can give a proof of this. It's an example of how you can sort of take advantage of the fact that you can work in the group algebra instead of in terms of matrices. Okay, so here's the proof, and this proof is sort of just using part of an argument from the Coutinho-Godsell book. Okay, so suppose e tilde theta of h is plus or minus e tilde theta of g, and the sign is given by sigma theta. Okay, then we can just find a polynomial with f of theta equal to sigma theta for every theta, right, by interpolation. Okay, then if we look at the spectral decomposition of A, then apply f of A is just the same as applying f to each of these eigenvalues. So f of A will be the sum of sigma theta e tilde theta of sigma theta e tilde theta. So then by the shape of f of A, and because the e tilde thetas are idempotent, it's clear that f of A squared will be the identity. Okay, and also that f of A g will be equal to h because f of g is just the sum of e theta tilde g's, and so f a of g will just be the sum of sigma theta e tilde theta g's. So that will be exactly h because e theta tilde h is sigma theta e theta tilde g, right? So that's clear. Okay, and now here is where we get a shortcut because we're working in the Cayley graph. Normally, f of A would be a matrix, and G would be a vector, and H would be a vector. But if we think of these things as being in the group algebra, then f of A is just an element of the center of the group algebra, and G is just an element of the group, and H is just an element of the group. So we can actually multiply both sides by G inverse. So we get f of A is equal to H G inverse. So then f of A is in the center of the group algebra, but the right-hand side, HG inverse, is in the group. So it's a central involution. Right. Okay, so here's the characterization of cospectrality in terms of characters. So two distinct elements, G and H, will be strongly cospectral if and only if there's a central involution such that the following hold. H is ZG, as we just saw, and for every theta, if you look at two characters that are in this x theta, they give you the same eigenvalue theta, then they have to agree. The sign has the value on the involution z has to agree in sign. So if chi of z is positive, then psi of z has to be positive, and if chi of z is negative, then psi of z also has to be negative. So that's the condition for strong cospectrality in terms of characters. Okay, so that's so much for strong cospectrality. Now let's move on to perfect state transfer. So let me just remind you of the definition. So the graph has perfect state transfer from G to H at time tau if the Hg entry of U of tau has absolute value 1. Okay, and so I'm now going to the perfect state transfer has been characterized for association schemes. I think starting in Gabriel's thesis, but also in the book with Chris. I'm just going to specialize that characterization to Cayley graphs. Okay, so here's the theorem. We have perfect state transfer in the Cayley graph between vertices G and H at some time, if and only if the following holds. First of all, the eigenvalues, those theta chi's, have to be integers. Secondly, G and H have to be strongly cospectral. And thirdly, if Z is the involution connecting G and H, then let's look at those eigenvalues corresponding to characters where the character is positive on Z, and phi minus are those eigenvalues where the characters are negative on Z. So if G and H are strongly cospectral, that's the same thing as saying that the phi plus and the phi minus have no intersection, they're disjoint. Okay, so the condition is a valuation condition on the two part of the eigenvalues. Okay, so for eigenvalues in the phi minus, we require that they all have the same two part. The two valuation of theta 1 minus theta chi. So theta 1 minus theta chi, those have to have all the same two parts. Right? And then for the theta chi in the phi plus part, they have to have bigger two parts, but not necessarily all the same, but bigger than the ones in the phi minus. Okay, so these are the precise conditions for perfect state transfer in Cayley graph. Okay, and so now I want to go out and apply this condition to some examples soon. But before I do that, I just wanted to mention one other thing. There's a minimum time t at which perfect state transfer happens, and that is 2 pi over g, where g is the greatest common divisor of these same numbers that we were looking at, theta 1 minus theta chi. Okay. And in the case of Cayley graphs, so this is sort of true more generally for association schemes, but in the case of Cayley graphs, this G, it also appears in discussions about instantaneous uniform mixing. So it's kind of an important parameter in this theory. But what we can prove is that any common divisor of the theta 1 minus theta chi divides the order of G. So this is this is without any assumption of integrality of the eigenvalues. So for any Cayley graph, any common divisor of theta 1 minus theta chi will divide the order of G as algebraic integers. So even in settings where we can't talk about greatest common divisor, right? So any common divisor will divide the order of G. Okay, so and the proof of this is just very similar to the abelian case, which is proved in a paper on uniform mixing of Cao, Feng, and Tan, which maybe Xiwan will talk about tomorrow. Okay, so let's look at some examples now and see if we can apply those character conditions to study perfect state transfer for some groups. Okay, so let's look at extra special groups first. So let P be a prime. So a P group is extra special if the center has order P and the G modulo of the center is elementary abelian. So the structure of extra special groups is well known. Every extra special group is a central product of extra special groups of order P cubed, and it turns out that for each prime P there are just 2 isomorphism types of extra special groups for any given order. Okay, so I mean there are many possible orders, but for each order there are 2 isomorphism types. So when P equals 2, the 2 isomorphism types of groups of order 8 are just D8 and Q8, and then every other extra special 2 group is just the central product of these groups. Okay, So let's consider. So the reason why we looked at extra special two groups is because well, previously we saw that if we want to have strong cospectrality in order to have perfect state transfer, we need to have a central involution. So the thing about extra special two groups is that they have a unique central involution. So we thought, well, maybe those would be the easiest groups to look at first. So that's why the easiest non-abelian groups to look at first. Okay, so so let G be an extra special group of order 2 to the 2n plus 1. They will have orders like that with the center Z of order 2. Okay, then we can easily calculate the characters, because the characters of irreducible characters of a central product are just like the irreducible characters of a direct product. Namely, you just take products of the irreducible characters of the component groups. But the only extra condition is that they have to agree on the central subgroup that you're sort of amalgamating, right? So what this means is that if you look at the character table of D8 and Q8, so D8 and Q8 have this property that their character table looks the same, right? You see that there's only one nonlinear character of degree 2, and it takes the value -2 on the center. Okay, so what that means is that for a extra special group, which is a central product of these things, there'll be just one nonlinear character. It will have order 2 to the n if you're taking a product of n of these D8 or Q8 groups, central product of n of them. You'll have a character of degree 2 to the n, and the value on the center will be -2 to the n, and the character will vanish off the center. Okay, so that's the character theory, and so now using the characters of the extra special group, we can see whether we have perfect state transfer or not. So so let's just check it. I have to choose a connecting set. So let me just choose S, the connecting set, to be a union of L non-central classes that generate the group G. So I choose them to generate the group G so that we have a connected Cayley graph. But let's just say we just take L of the non-central conjugacy classes. So each of the conjugacy classes is of the form G times GZ, just of size 2. And the phi minus, these are the eigenvalues corresponding to characters that take a negative value on Z. There's only one character that takes a negative value on Z, and that is the nonlinear character. Okay, but Z is not included in my set S, and that nonlinear character vanishes on everything outside Z, outside the center. So so that means that the eigenvalue corresponding to it will be 0. Now let's look at the characters of G mod Z. G mod Z is an elementary abelian group, and so each element of the elementary abelian group gives you a character by taking -1 to the dot product. Okay, so let S bar be the image of S in G mod Z, then and let E sub Y be the number of elements in S bar such that the dot product with Y is 0. Right. So then easy computation shows that the eigenvalue corresponding to this character lambda sub Y will be well, you sum over all the elements in S and you apply that character. So summing over the elements in S is just the same as taking 2 times the sum over S bar. And so you get 2 times, and then you just do the computation. You get 4EY minus 2L. And so so phi plus will be 4EY minus 2L. Okay. Now the condition for cospectrality between an element H and the element G, which is ZH, or two elements connected by Z, the condition for cospectrality is just that the phi plus and the phi minus are disjoint. So we would just want E sub y not equal to L over 2. Okay. Then we have those two valuation conditions for perfect state transfer. Oh, yeah, of course, the eigenvalues are all integers, right? So we have the integrality condition. So we now consider the valuation condition for perfect state transfer. If we look at the valuation of theta 1 minus theta psi, that will be, well, theta 1 is 2L. Theta 1 is the size of S, which is 2L. Okay, because each conjugacy class has size 2, and we're taking L of n. And then theta psi is 0, right? So it's just a two valuation of 2L, right? And for the y's, the valuation of theta 1 minus lambda y, well, again, it's just 2L minus 4e minus 2L, so it's 4L minus 4ey, right? So so what we want is for the valuations in the phi minus ought to be the same. Well, that's going to be trivially true because there's only one element in phi minus, and so it's the valuation of 2L. And we want the valuation of the things in phi plus ought to be bigger than the valuation of 2L. Okay. So if L is odd, these will be satisfied, because if L is odd, then the valuation of 2L will be just 1, and then the valuation of the other things will be bigger than that because they're all divisible by 4. Okay, and moreover, if L is odd, E sub y can't be equal to L over 2 because E sub y is an integer. So the condition for cospectrality will also be satisfied. And as I said, the integrality condition is satisfied. So we have perfect state transfer in this Cayley graph for this set S. So that's just an easy example of how you can get many generating sets, connecting sets S that give you a Cayley graph with perfect state transfer for extraspecial groups. And you can find the precise conditions on S, which is worked out in our paper. But I don't want to go into that. Okay, so that's the first example, extraspecial groups. The next example I want to consider are the Heisenberg groups. So, the things I'm calling the Heisenberg groups are slightly different from the things that John Yard called Heisenberg groups. They're sort of the same when n is equal to 3 and q is equal to an odd prime, right? But otherwise, they're slightly different. Okay, so Hn of Fq will be the group of matrices of this form. So this is not really a 3 by 3 matrix. It's an m plus 2 by m plus 2 matrix, because the thing in the middle is the identity matrix of size n, and the V transpose is a row vector of length n, and the W is a column vector of length n. Okay. So just the matrices of that form. So of course the center of this group will just, if you easily do the computations, the center will just be the things where the V and the W are 0. So so the center has size q. And these matrices is easy to compute. The non-central conjugacy classes also have size q, and they're the cosets. Okay. Now we look at the characters. There are two types of characters. First of all, the linear characters, the characters of G mod Z. And then for each non-principal character of the center, there's a non-linear character, psi sub mu, whose restriction to the center is just q to the n times mu. So these psi sub mu's have degree q to the n, and they vanish outside the center. So very similar to the extraspecial case. Okay, so here's an example of the character table of H1 of 4. So this is just the group of 3 by 3 upper upper unitriangular matrices over the field of F4. Okay, so you can see that we have 16 linear characters, and then we have 3 nonlinear characters of degree 4, and they vanish. So these dots are zeros. This is by the way a character table output by gap. Yeah, I might as well explain a little bit about these character tables. So the top row, 1A, 2A, those are the names of the conjugacy classes, and the 2 means it's of order 2, 4 means it's of order 4, and so on. Okay. Above that, there's a row of numbers. Okay, the 2 is the prime 2, and then the other numbers following it are the exponents of 2, which occur in the centralizer of that element. Okay, so for example, 2G has a 4 above it. That means that the centralizer of an element in the class 2G is of order 2 to the 4. Okay, and so the size of the conjugacy class 2G will be the group order divided by 2 to the 4, which will be 2 squared, right? 4. So each conjugacy class will have size. Each of these conjugacy classes on the right will have size 4. Right? The non-central conjugacy classes will have size 4. Okay. So let's choose our connecting set now. Let's just pick an involution in the center, and take S to be well, we take S to be the union of this involution, and then we take a union of L non-central conjugacy classes. We want them to generate G to get a connected graph, and we want the whole union to be self-inverse in order to have a not an undirected graph, right? So, but other than that, arbitrarily choose those conjugacy classes. Then theta 1, the number of elements in the set S, will be QL plus 1. So 1 for the Z and Q for each of the L non-central conjugacy classes. And for the characters of G mod Z, the linear characters, we'll have that theta sub lambda will be congruent to 1 mod Q. The 1 comes from the Z, and then the mod Q is because each conjugacy class has Q elements in, right? And the characters are constants on conjugacy classes. So, well, they will be in the yeah. So you get 1 mod Q. So I only care about mod Q. I don't care about the exact value. Okay, and then if psi is a nonlinear character, well, it depends on whether Z is in the kernel or not. If I don't mean psi of Z is equal to 1. I mean if psi of Z is positive, that's a misprint. So let me see. So this is equal to it's positive, right? It's positive. Then theta psi will be equal to 1, and that's because psi vanishes on all the elements of S except for Z. So theta psi is just psi of Z divided by the degree of psi. And okay, so this is negative. So you should say negative. It's positive. This is negative. Then theta psi is equal to -1. So now we can check the condition for cospectrality. The condition for cospectrality is that the phi plus and the phi minus should be disjoint, and indeed they are, because the phi plus are the lambdas and the ones where the value on Z is positive, and they both are congruent to 1 mod Q, and the one for the negatives are congruent to -1 mod Q, and Q is not equal to 2. So those two sets are disjoint. Okay, and so the condition for cospectrality holds. And then we can check the condition for perfect state transfer. Well, if we look at theta 1 minus theta chi, will be 0 if if mod q if chi is in phi plus, and it will be 2 mod q if theta chi is in phi minus. So the valuation condition for perfect state transfer is satisfied. So we have perfect state transfer for all such connecting sets. Okay. So the third example I want to look at are what are called Suzuki Two Groups. So the Suzuki Two Groups are the ones I'm talking about here are the CELO two subgroups of the famous simple groups discovered by Suzuki. Okay, so Suzuki two groups were defined more generally in a paper by Graham Hickman called Suzuki Two Groups. But among those are these Suzuki two groups that appear as CELO two subgroups of those simple groups. So let's look at how they're defined. Let's choose an odd number n, and we look at the field of 2 to the n elements. Okay, and let f be the squaring map on that field. Then, because n is odd, f will have a square root. Okay, there'll be a field automorphism whose square root is the Frobenius map. And then you just define G to be the group of matrices, 3 by 3 matrices, where you look at 1 x y, and then we put sigma of x in the other end thing here. So you get a group of matrices this way, and this is a group of order q squared, where q is 2 to the n, right? So you have q choices here, q choices there. The center is of order q. The center is the one are the matrices where the x is 0. And G modulo the center also has order q. And this group has the interesting property that all the involutions are in the center, right? Okay, and you can carry out a similar analysis to the Heisenberg case to show that that we have perfect state transfer for many choices of connecting sets S. And I sort of leave this as an exercise because if you do this exercise, you'll probably quickly learn how to find perfect state transfer in groups by inspecting character tables. So this is the character table of that group. And you can see it looks very similar to the character table that we had for Heisenberg groups. Okay, we have these characters in the center, these characters that are supported on the center. Well, they're not quite supported on the center because there are these elements here where the value is 2i and minus 2i, 2i and minus 2i. But remember, when we take our S, we have to take S to be inverse closed. And for example, class 4e and class 4f are inverses of each other. So they both have to be in S together. So when we sum to calculate the eigenvalue, their contributions cancel out. So it's effectively as if we had zeros here, right? And then you can do the same argument as we did for the Heisenberg groups, and you see that we'll have perfect state transfer if we choose S to be, for example, a fixed involution in the center and any inversion closed generating set of non-central classes. Okay. So those are 3 examples of families of non-abelian groups where you can find lots and lots of connecting sets that give you perfect state transfer. Okay, so let me move on to the topic of uniform mixing now, as this is the main theme of this conference, one of the 3 themes. So let me just remind you, the Cayley graph has instantaneous uniform mixing at time tau if all the entries of u of tau have the same absolute value. which has to be 1 over the square root of the order of G. Okay, so if we take the spectral decomposition of A, then U of T will be just the sum of e to the I T theta chi e chi. And so its xy entry will be, well, we have a formula for e chi, right, from before. And so we could calculate the xy entry, and this will be it. So if we want u of t xy to have absolute value 1, we want the right-hand side to have absolute value 1 for all x and y, which is the same as saying that it has absolute value, that this thing has absolute value square root of g for all g and g. Okay. So that's the sort of necessary and sufficient condition for the Cayley graph to have instantaneous uniform mixing at time tau. Now, the above condition is a condition on the columns of the character table, because you're summing, you're picking the elements, an element G, and then you're summing down all the characters. So this is a condition on the columns of the character table. So for fixed G. Okay. So there's a sort of dual condition on the rows, which is in a paper of Ada's. So you have instantaneous uniform mixing at time tau if and only if there exists complex numbers of absolute value 1, and we assume that so we want this expression to be e to the I tau theta chi times the square root of g. We want this expression to be that. So we want, but we require that the coefficient of ti is the same as the coefficient ti star, where I star is the inverse conjugacy class, right? Okay, so you want the coefficients for the inverse conjugacy classes to be equal. Then if this is the case, then the matrix let me see, the matrix, the sum of I of ti ki. So where we think of the ki as being the sum of the conjugacy class elements, and then each conjugacy class sum is multiplied by the coefficient ti, and then we take the regular representation of that. So we think of this as a matrix. Well, this matrix will be the complex Heisenberg matrix, right? So that's condition for uniform mixing, expressed in terms of the rows of the character table. Okay. So these conditions are, of course, related by the orthogonality relations. So if the t's exist, then you can calculate what the t is. The t is exactly the value of this sum here, right? So the absolute value of the sum is square root of g. So this value of this sum is square root of g times some element of absolute value 1, and that element is ti. Okay, if the g is equal to gi. Okay, so we can sort of weaken the conditions a little bit and get conditions for we get a pair of dual conditions for the center of the group algebra to contain a complex Hadamard matrix. Okay, so this is also based on Ada's paper. Okay, so the center of the group algebra will contain a complex Hadamard matrix if and only if one of the following conditions hold. So I guess the point is, as Ada pointed out in her talk, there are sort of two steps to uniform mixing. First of all, you try to find a complex Hadamard matrix in the Bose-Meson algebra, and then you try to find if you can find T so that you can the exponential is equal to that complex Hadamard matrix. So these conditions are for finding complex Hadamard matrices in the Bose-Meson algebra, or in this case, the center of the group algebra. And let me see. Yeah. So don't forget the complex Hadamard matrix. If you find these TIs, then the complex Hadamard matrix will just be the sum of the TIs times the KIs. And in particular, the regular representations of the KIs are sort of 0, 1 matrices, and so if you can find the TIs that are actually plus or minus 1, not just the absolute value 1, but plus or minus 1, then the complex Hadamard matrix that you get will actually be a Hadamard matrix. Okay. Okay. So now I want to apply these conditions to some examples. Okay. So first of all, condition 3 immediately implies that the support of chi is greater than or equal to the square root of g. Let's go back to condition 3. See, so condition 3, this right-hand side is just really, if I take absolute values, then that's just going to be the sum. That's going to be less than or equal to, by the triangle inequality, the sum of chi, sum over I of chi of ki over chi of 1, which is really just the sum of sum over the group of chi of g over chi of 1. Okay, so that number will be less than or equal to the size of the support of chi. Okay, so if G is an extra special P group or a finite Heisenberg group, then it has a character that is supported on Z of G, so vanishes outside Z of G, and Z of G is smaller than the square root of the order of G. Right. So we see immediately that there's no complex Hadamard matrix in the center of the group algebra. And so we can't have instantaneous uniform mixing at any time for these Cayley graphs. Okay. If we look at the Suzuki Two Groups, we can't eliminate it this way because the center of G is just exactly equal to the square root of the order of G. Right. So and also the characters don't quite vanish off the center anyway. So and in fact, there turns out to be a complex Hadamard matrix, many complex Hadamard matrices in the center of the group algebra, which let me show you how to get these. Okay, so the condition is that we want complex numbers of absolute value 1, so that when we use them as coefficients to look at the chi of ki over chi of 1 and sum them up, we get something which is length the square root of, sorry, this is condition 3, length is something which has absolute value the square root of G. Okay, so this is the condition we're going to use. So we're going to try and pick, look at the character table and try and pick the TIs. Okay. Right, so we look at this character table. If I choose coefficient 1 for all of these classes in the center, okay, and then for these non-central classes, I choose some alpha and minus alpha, and here a beta and a minus beta, and a gamma and a minus gamma. I just choose them to be opposite sign, but otherwise arbitrary. Then when I sum these things up, I'll get these will all be 0. This block here will give me 0, and here I'll get 1, 2, 3, 4, 5, 6, 7, 8, which is the square root of the group order 64. Okay, whereas for these characters here, if I am taking 1, so when I add them up, I get 0. I'll get 0 contribution from this part. Yeah, that will be 0. These will be 0. And here, because I've taken opposite signs, I'll get I'll get a 2i and a 4i, but then I have to multiply by the size of the conjugacy class, which is 4, and I have to I have to look at chi of ki over chi of 1, right? Which is the size of chi of gi divided by chi of 1. Right? So here I'll get 4 times 2i, that's 8i divided by 2, that's 4i. So I'll have a 4i times gamma, and then another 4i times gamma, that's 8i times gamma. So that will have absolute value 8, which is again is the square root of the group. So I get for each of these choices, I get a complex Hadamard matrix in the center of the group algebra. And if I just simply choose them to be plus or minus 1, I just choose this one to be plus 1, minus 1, plus 1, minus 1, plus 1, minus 1, and so on. Then the thing I'll get will actually be a Hadamard matrix in the center of the group algebra. Okay, so hopefully this illustrates the purpose of my purpose in trying to get things in terms of characters, so that we can sort of just get by inspecting character tables, we can check for these phenomena. Okay. Okay. So okay. Okay. So that's okay. Oh yeah. Okay. Right. So the reason why we have a complex Hadamard matrix in that center of that group algebra, but no uniform mixing, is because I chose negative opposite signs for the A and the A minus. But for uniform mixing, I'm not allowed to do that. Remember, the TI and the TI star have to be the same. So I can't. So there's no. That means I won't be able to get instantaneous uniform mixing. There's nothing clever you can do with the other coefficients and so on to get it. So so you can show that there's no instantaneous uniform mixing. Nevertheless, you have a Hadamard matrix inside the center of the complex group algebra. And this example, this is the Suzuki group based on a field of size A. This example generalizes completely to all the Suzuki Two groups of that type. So we have a whole infinite family of Hadamard matrices. And I know we have some world experts in the audience on Hadamard matrices. So I'm hoping that maybe they can tell me what kind of Hadamard matrices these are, and where else they occur, and so on. Okay.
So Peter, I think it's about time, 15 minutes.
Okay. Yeah. Okay. Yeah. So I'm just about finished. I just want to tell you my problems. Okay. So one problem is just to find an example of instantaneous uniform mixing in a non-abelian group, or even better, an infinite family of examples. Another problem is to find more complex Hadamard matrices in the center of group algebras of non-abelian groups. And the third open problem would be just to find more examples of perfect state transfer in non-abelian groups. So I don't know any examples in other than in two groups, or in dihedral groups, or in direct products of things which already have perfect state transfer. Okay, so yeah, that's all I wanted to say. Thank you very much.
Thank you. Thank you for a very interesting talk. Any questions?
I have one very simple question. So the CLF2 subgroup of the Suzuki groups, they're nilpotent, class 2, is that right?
That's right, yes. Well, in fact, yeah. So yeah, all of the groups that Higman constructed that he called Suzuki Two Groups, they're all nilpotents of class 2, yes.
Yeah, okay, thanks. Okay, I will make one comment then. You were asking about Hadamard matrices in the center of a group algebra, basically.
Yeah.
Now the there's basically a general question about taking association scheme. What are the type 2 matrices in that scheme? What are the flat type 2 matrices in those schemes? And there's a good reasons for thinking that viewing those matrices as being essentially analogs of bent functions that the cryptographers work with.
Mm-hmm.
So it's a it's a natural problem with lots of ramifications.
Oh, okay.
And not particularly easy.
So I have
Yeah.
a question. In the examples that you've looked at, have you seen sets of larger than like size 2 of pairwise strong cospectral vertices?
Well, these are examples with only one central involution, right?
Oh,
No,
right,
no.
right.
No. I mean, if for any so for any involution, you can get in those examples,
No.
you fix any
Is
involution.
there a subgroup of order 4 where each element gives the elements in that set, or subgroup of pairwise strongly cospectral? So in other words, if we have two involutions A and B that are cospectral with 1, we want the product A B to be cospectral with 1.
I see. I have to think about that. I'm not sure.